Yes, good evening, everyone. This is our eighth problem solving session for the Aqueous Corrosion and its control course. So this week we don't have any to discuss. I'll just go over any doubts you have, or maybe go over the theory a little bit, Aqueous Corrosion and wetting corrosion. Uh,
Can we discuss question number 5 of last assignment once again?
Question 5. And let me just get it. Point out the incorrect statement.
How option 1 I want to discuss, if there are two metal in the galvanic coupling and both the
Mhm.
metal are noble with respect to the cathodic reaction, say if the hydrogen evolution reaction is taking place and both the metal are noble with respect to the cathodic reaction, then whether any of the metal will corrode or not in the if there is a galvanic couple.
Mm, yeah, if you're assuming both of them are noble gold or platinum.
Gold, platinum, or titanium, or platinum, or gold, or silver. If both the metals are having their
Mhm.
potential positive with respect to the cathodic reaction which is taking place in the system, then whether
Mhm.
any of the metal will corrode or not.
I don't think they should corrode.
So then the first option I think should not be there if that is the case.
Yeah. Mhm. Let me just Google it. Both of them are novel. Still one of them is right.
Because in that case the hydrogen reaction or the oxygen reaction will act like an anodic reaction with respect to both of
Mhm.
them.
Mhm. So if they are both noble, in this case, One of them is not suffering higher corrosion. I think so. I mean,
Whether Evans
doesn't
diagram will be possible for such cases when where both the metal are noble? How Evans diagram will be done if both metals are noble with respect to say hydrogen evolution reaction, and
Mhm.
both the metal are immersed in uh, say mild acidic solution, then I don't think that that equilibria of H plus reaction and metal
Yeah, yeah.
reaction will be possible, thermodynamically possible.
So in that case, wouldn't the statement be incorrect still? Like, if that's you have gold and platinum, for in that case, there's no corrosion reaction taking place. So this statement, like one will suffer higher corrosion rate, it would be incorrect, right?
Oh, it is given incorrect. Then that's
Yeah,
okay.
yeah,
That's okay.
yeah, yeah. And you also had two questions, like in this, since you're asking questions, you can go like in ICCP, what reaction is taking place at the anode surface to balance the charge
Yes,
transport.
yes.
Yeah,
From the last session, I requested
yeah,
you to
yeah,
discuss.
yeah. What I found was if it's in the sea, most in case of sea, there's probably the chlorine chloride ion in the salt would get reduced and become chlorine gas. And similarly, if it's underground, the your noble anode, if it's underground, uh, the reaction would be oxygen evolution reaction. So that would balance the charge transport. So the question was just to, for others to know. In ICCP, what reaction takes place uh, on the uh, surface of a noble anode to balance the charge transport. So, like in this case, the noble anode is protecting the hull of the ship. So, and the anode surface can be like titanium, like that, titanium. I thought like if it's platinum usually, yeah, it's like acting as a catalyst for the reactions to take place. So it tells no take part in taking part in the reaction. That's another reaction taking place. Right. Yeah, that's what I found. Chemical reaction. Yeah. And low stability conditions. NMO titanium. Metal oxide catalyst. Titanium substrate and metal oxide catalyst on the same page. There's a typical node used. So, okay, does that answer your question?
And how events diagram is being drawn for such sort of system for ICCP case?
Hmm. Can we make events diagram if the reaction is taking place in different places? Did we have it? We had that in case of sacrificial. I think on the metal side, it probably looks something like this. And here, we are applying external voltage to suppress the corrosion. And on the other side, I'm just thinking like, what's the reduction potential for that? The platform would be to
Actually, in this case, what I think the potential of the anode, unlike in the case of galvanic, where the potential of the anode is negative with respect to the metal which is protected. In this case, the anode is an inert anode, so the potential will be positive with respect to the metal which is being protected. Some different sort of diagram will be drawn in this case.
yeah. This would probably be the diagram for the metal at cathode. Peaker wouldn't be this. This is fine. Okay. Yes, that would be shifted even. Not sure. And definitely increasing like on the anode the reaction, the hydrogen evolution, the oxygen evolution reaction would rate should increase. You have to see where the reduction.
Yeah, node in case of this ICCP, because it is relatively inert with respect to the cathodic reaction, which may be oxygen reaction or the hydrogen evolution reaction. So, no even diagram can be constructed between the hydrogen equilibria and the metal equilibria of the inert anode. That will be thermodynamically unstable. So, the possible equilibria in this case is that the reaction which you told, that chlorine reaction or other ionic reaction. So how that will be plotted on the event diagram?
Yeah, since that's the only reaction taking place, the metal won't be getting oxidized. There are diagrams for cathodic coating, but
If required, we can discuss this in the next class. We can discuss the assignment which is due tomorrow, so that if any confusion is there, we can clarify it today itself, so that we do not lose mark on that.
yeah, sure. Maybe you can ask this question to Professor. That would be. And is there going to be another live session? Any updates on that?
Yeah, I am aware of that. I will.
Like, did they tell us anything about if there is going to be another live session with the professor or not? I don't know. Not up to date with the announcements. Okay, there's okay. Day after tomorrow, yeah. But it's again going to be on YouTube. Okay. And you had another question. In case of Aqueous corrosion, what would happen to Fe2 ion concentration? Nice. So I got two answers. So where is this? From corrosion, you get Fe plus two ions. They now they can react with the water form of hydroxide plus you get ARH plus iodide. One thing that happens is this Fe iron hydroxide, this gets diffused and gets deposited on the mouth of the air crevice. When diffusing, it gets forms of film deposit on the mouth of the air crevice. Another thing is you'll also when the chloride migrates in, you can also get iron chloride, Cl2, and that can also diffuse out since the concentration here is higher. Uh, Again, the device is still open to some amount of diffusion, like even though oxygen Okay, so if you're removing oxygen, if water has very low solubility of oxygen, so concentration of oxygen in the solution is low. So during according to Fick's law, like uh, rate of diffusion J is equals to minus D, yeah, dx, concentration by dx. So this gradient would be much larger in case of iron. Yes. From corrosion, we get much higher concentration of iron chloride or higher, iron hydroxide. So due to higher concentration, the diffusion might be significant enough. That's removing the iron ions, sacrifice, avoid forming inside the phase. And we had a question like, what would happen? Does corrosion will depend on the metal hydroxide solubility because dissociation of solubility. Again, mm, if it's less soluble, this equilibrium would move forward, right? More of the hydroxide would get, the iron would get converted into hydroxide, and your pH would decrease. So what I found was the pH would decrease further. So if your hydroxide is can easily dissociate, your pH will be lower, and then otherwise corrosion will be more. Hope these make sense. So, like you can discuss. We generally discuss like what factors influence the pitting and device corrosion. And that will be helpful for you to answer the questions. Right. In device. Right. So factors affecting device corrosion. Geometry is one. So as we decrease the width, we are limiting the diffusion. Right. Diffusion of the oxygen inside the device, and that's preventing formation of the so decreasing decreasing width, reducing O2 diffusion, which is increasing the corrosion of device. And similarly, now if you had a flowing water over it, you'd have bit higher diffusion of oxygen inside the crevice that would decrease the corrosion. Flowing a stagnant water would also increase the crevice corrosion. this. Other factors are like oxygen content in the water, pH, presence of fluoride ions, temperature, agitation. As pH decreases, surface motion increasing, temperature increases, the diffusion increases, and then your maybe diffusion is not the main reason. Fluoride ion again attacks the passive layer and increases the corrosion. Type of gasket selected. So if you have a gasket which absorbs water, I guess it absorbs water would be more prone to crevice corrosion. This and if you're able to reduce the crevice completely, like copper welding or things, then you can reduce again crevice corrosion. So you can apply sealant to isolate your crevice. So as your autocatalytic, it means as you're increasing okay, so this is your crevice which is forming. So here your metal is getting outside, so iron plus 2. What's happening is iron F2 reacting with water to give you iron hydroxide and H plus. This H plus is making the environment inside the pit more acidic. So pH is decreasing. Since pH is decreasing, that's increasing your corrosion rate. So this reaction goes even more further. So your reaction metal P is 2 Fe plus 2 electrons. Right. So this leads to this, and this leads to more corrosion. So that's what meaning autocatalytic. Autocatalytic is self-catalyzing in a way. So once the reaction starts, it's uh, helping itself progress faster and faster. Yeah, so it's self-propagating or have a positive feedback loop of time. Yeah, that's what it means. Autocatalytic instead of reaction. Then there is some regarding device corruption. An example copper exam. What kind of alloy you're choosing also affects device corruption. So 70-30 copper nickel alloy is not prone to device corrosion, and stainless steels are. So compared to those, it's more prone to corrosion, device corrosion. And we had effect of different alloying elements in the steel. And adding chromium, molybdenum, and nitrogen in the steel improves device corrosion resistance. Yeah, whichever. This is the best, the most device corrosion resistant metal. And then stainless steel you can compare depending on the concentration of these metal and of these metals, which is more resistant. The last one, yeah. I think that should cover what time. The questions asked in the assignment, like what factors affect the device person. Now we can discuss fitting. Mm,
I request you to discuss the questions of the assignment which is tomorrow.
do you have any specific question like you want to answer? Me to answer, like help you?
There are 10 questions. I request you to discuss all the questions.
All the questions. I've already like answered most of them. Like
So the
first one
assignment
is
which is due tomorrow, I get to discuss.
yeah, assignment week 7 and 8, right?
Yes.
The first question is about autocatalytic nature of device corrosion. So I already told you like As the metal is getting dissolved, it's forming metal hydroxide that is increasing the hydrogen ion concentration. So the pH will become more acidic. And what else? For the crevice corrosion, you want stagnant water, right? You want lower diffusivity of diffusion of oxygen. I think that relates to the last question. If you have a stagnant and flowing NaCl solution, which will have which will fail first. Yeah, if you're in the stagnant solution, you'll have lesser diffusion of oxygen and more crevice corrosion that will fail first. And crevice corrosion great question. Now we have following statement is incorrect. Here again, the gasket which can absorb water is more prone to crevice corrosion. So, I think it's mentioned in the slide. Mm, yeah, that's fine. So you want to have to prevent crevice corrosion, you want the solid non-absorbent gasket, whichever is better. Uh, and comparing the stainless steel and the copper nickel alloy, so the copper nickel alloy is more resistant to crevice corrosion. And if you want to compare two different metal stainless steel grades, the one which has more, like in this case, everything is equal, just the molybdenum, one has more moly and other has less. The molybdenum increases resistance, so that's more resistant. So the crevice corrosion part of the assignment, I think I have answered. I can discuss that about more over the fitting corrosion. So fitting, what are the factors that affect fitting? Hmm. Moving through the slides and whatever factors it's a little bit up. So factors which are affecting the pitting corrosion, one is depth of pit. If pit is stable, that means your pitting corrosion will happen or more. So you want a stable pit. So stable pit means chemistry, the chemical environment inside the stable, the pit is stable. That's why you also want stagnant water. If you had moving water, uh, any increase in the metal, the pH here would get washed away and that pit would, the chemistry inside the pit would get destroyed. So for pitting corrosion to take place, it should be stable. And so if you increase the depth, If it will be more stable, fitting corrosion will increase. Okay, so pitting tendency, yeah, about electrochemical factors. Yeah. Factors which are influence the pit. E passive, if you have E pit, yeah. If you have higher E pit, that increase that reduces their pitting tendency to pit from pitting corrosion. You want higher E pit. You also want higher repassivation potential wherever this curve intersects. Let's say repassivation uh, potential. You want that very high as possible. As high as possible. And these are the elements that help it help. And I think we talked about surface roughness. So surface roughness actually increases your fitting. And if your equilibrium metal potential is high, so if metal is more noble, it's less prone to fitting corrosion. And surface area. Uh, okay, and since fitting is a stochastic mechanism, so like depends on the probability. So if you have higher surface area, you'll have more probability of having defects which promote fitting. So if you have larger surface area, it increases your chances of getting fitting corrosion. Uh, and if you want to check what else, fitting, it's more aggressive ions like chloride, they reduce your fitting resistance, so increase fitting. So that's affects your fitting tendency, your depth, as I mentioned already, affects your fitting tendency, applied potential. Yeah, if you're making metal more noble, that will affect your fitting potential. So and then there was what was that? The prime number. If you want to compare different steels for their pitting corrosion, you can use this prime prime number. So this is a percent chromium, so percentage CR plus 3.3 into your percentage of molybdenum plus 0.5 into percentage of tungsten plus 16%, 16 times percentage nitrogen. So you can use this one. So if you had Fe 18 Cr 10 nickel, and 1 nitrogen, your prime number would be 18 for Cr, so 18 plus 3.3 to moly, so that's 2%. Plus 0% tungsten plus 16 times 0.1. 18 plus 6.6 plus 1.6 to 26.2. So you can apply this formula for all other the stainless steel grades as asked in the question. Okay. Yeah, I'll upload it right after the session. So, any other questions like regarding tomorrow's assignment? I think that covers all the. There's one question about you have different metals chlorides, tin chloride, iron chloride, silver chloride. The third one, yeah. So your pitting tendency, if you're increasing your E-pit, this is your E-pit, you're reducing your pitting tendency. Okay, so if E-pit is high, your pitting tendency E-pit increases, your pitting tendency decreases. And equilibrium potential of the metal is high, so the equilibrium potential of metal, so that's how noble the metal is. For example, platinum has 1.2 plus 1.2 volt reduction potential, and your iron is 0.44. But I think in this case there means something else. So here they're talking about this plot. And this is your equilibrium potential. So as you're increasing your equilibrium potential further away from this E pit you are, safer you are. You'll have less chances of getting E pit, no pitting. So if equilibrium potential is low, uh, E equilibrium is low, your pitting radius. And that's a clean potential of the head. But yeah, if your equilibrium potential is high, you should get more pitting corrosion, and this option should be correct. The solution I have is they've not mentioned it. Maybe they're talking about the mobility of the metal. So platinum has a 1.2 volt plus 1.2. Fe is 0.44. In general, this would be more prone to corrosion. Yeah. Repassivation potential. Okay. Right. This is your repassivation potential. E repassivation. This increases. This increases. Your pitting tendency decreases. Okay. Surface roughness. I think you mentioned in the class. Surface roughness increases. So roughness increases. The pitting tendency also increases. Finally, surface area is low. That's this case. Since it's a statistical stochastic effect. So it's the initiation of the pitting, like it's a mm, microscopic phenomena, so kind of random, like where the pitting will happen. And if you have a small sample, you have less probability of getting this initial defect where the pitting will happen. If you have a larger section, you will have more probability of these uh, pit initiators to take place. So as you increase the uh, s- specimen size, the probability of pit occurrence of pit increases. So, pit has low surface area, pitting tendency will increase or decrease. Sorry. The surface area increases, the pitting tendency increases. And for the second one, you just have to see um, which ion is more positive and uh, better oxidant. Will cause oxidation of the metal. So which has the most positive potential will be the most strongest oxidizer. Anything else? Hmm, There is a slide. So cold work reduces the pitting resistance. Cold work sample and to have more defects so that they will increase your pitting. Alloying element. Great. Smooth surface favors better passivity and surface of surface. Surfaces are more prone to pitting. If you have high flowing water, just flowing solution over your pit that disturbs the pit chemistry and that doesn't allow progression of the pitting. Okay. We had this slide where we discuss about applied potential. So you're increasing your applied potential, your pitting tendency is increasing. Second one, yeah. Second one is just about which metal ion is more oxidizing. So you just compare the E naught for different metals. So E naught for Fe plus 3 Fe is minus 0.037. For Ag plus 2 Ag, it's plus 0.79 minus 0.99. So this has more. This wants to become silver again. This is more reducing uh, tendency. So what will happen is this reaction will take place. Now, Ag plus, we will have P plus 2 and you will get Ag. So whichever has the highest reduction potential, and if you calculate the delta E naught for this reaction, this will be the most favorable reaction. So it will be more favorable reaction compared to this. So that's how you can decide uh, which solution will be most susceptible to pitting. I'm trying to see if I can justify the pitting tendency of metal increases if the equilibrium potential of the metal is high. According to me, it should be. But for some reason, the solution I have, and this is the solution they've been following since the beginning of the course. That said, the statement is incorrect. Since the statement is putting the C. Yes, yes. It's the first option. This one. Yeah, that's what I. It's equilibrium potential is close to your fitting potential, you'll be more prone to fitting corrosion. Okay, you guys can answer what you feel. Maybe they have marked their own answer. We can ask on the form, or I can just the DA correct it later. Okay. So answer based on last year's question, last year's answer. Answer based on what is right. I think this should be true. If you guys don't have any other question, you can end the session here. Okay. Thank you all for joining. See you next week.